All right, looks like we're live. On today's edition of Mark Voids a Warranty, we've got a thrift store find, a Singer sewing machine. Now, this particular machine is capable of all sorts of stuff, including, and not limited to, embroidery, which is kind of cool. You've got all these little cards down here that indicate some of the different patterns it can do, which is great, except the machine doesn't turn on. But there should be a lot of interesting electronics and whatnot inside, so we're going to open it up and, see what's there. And whenever you're taking something apart, usually the best thing you can do is just start with what's visible. Find screws. If you don't know if they're case screws or whatever, just start with those. And although I won't be using it today, I have set up my torque limiting screwdriver. Just if you ever want to put stuff back together and have it stay together, you want to make sure that the screws are properly torqued. One of these little guys will get you there. All I'm doing is starting with the big screws that look like case screws. And after I make a little forward progress there, I'm sure there's going to be a few more surrounding the case that we'll need to get a hold of. All right. So the first thing that fell off was just a back cover, which kind of looks kind of cool. But it's also got this indexed instruction manual, which gives the different stitches that are available and all that. I kind of like it. That's neat. We'll set that off to the side and see what else there is to see. Thread tensioning bobbin stop for bobbin winding. Looks like we have a few more case screws. That one's loose. That's loose. Let's see what else we have. Looks like there's one more here. Can't really see what I'm aiming for. There we go. Usually you can hear the screws skipping once they're completely free. And just in case there is something else going on here, we'll loosen up that bobbin cam. That is there to control when the bobbin is full once it's wound. Get that out of the way. And the tensioner. Set that off to the side. See what else there is here. Oh, looks like we've got screw hiding up in here. There goes the cover. And while we're at it, a couple of case screw looking things down here at the bottom. Whoops. All right, we have exposed a little bit of circuitry and a little bit of the mechanical systems, but we will, I'm sure, dig into that once a little bit more of this has been revealed. Very interesting stuff. Again, all I'm doing now is looking for the obvious little bits, the screws that are visible and easy to get to. A lot of these self-tapping thermoplastic screws are holding this particular device together. They're pretty common when you take stuff apart. But every time you look, there's always a little something you missed. So if you start applying pressure and something doesn't really want to give, there's usually another screw there that you weren't paying close enough attention to. Another thing I always do is kind of feel the stickers, see if there's anything hiding underneath them. You never know. Sometimes there are. So something interesting down here. There is a screw. It's like a leveling foot, except this is knurled. I mean, it's meant to be moved by hand. Let's see if we can't bring this up on the close-up cam. Interesting one, but what are you going to do? All right. Let's keep taking stuff apart. And see what happens. Ooh, okay. We've actually found use for our torque driver. Now, I'm not putting this thing back together, right? But I'm using a torque driver to take it apart. This particular one kind of has some bidirectional functionality. It's was calibrated a long time ago. It's nothing new. But it lets me know that these particular screw heads are put in a little stronger than the rest. So, let's see if we can't make some adjustments and figure out how much force is needed to break these things free, just in case we ever have to put them back. We can do that. And it looks like for this particular driver, we're at the limit. So it will take more force than I'm able to properly record to loosen these screws. There we go. So if I ever had to put this thing back together, I don't really have a measurement for how much force would be needed. I would just have to crank them down. And even with my little handheld screwdriver here, it takes quite a bit. So again, all I'm doing now is removing everything that is visible, and hopefully that will let me start getting into the guts of this. Some of these, it just doesn't matter, like the leveling feet. You just want to give them a good crank. They're not really structural. You just don't want them to back themselves out anytime soon. So let's see if we can't break these, and then I'll switch back to the torque limiting screwdriver. All of this, of course, is outside the purview of the electrical engineer. This is all mechanical engineering. However, a sewing machine, especially one that has some embroidery functions, is decidedly an electromechanical device, right? You would need a team that can make sense of multiple systems. You're not going to find a mechanical engineer that can do this, or an electrical engineer that can do this, not all on their own. This is a group project, except unlike the group projects you remember, this is a group project done by winners, right? All right, so here is what we've opened up so far. We've just taken the bottom off, and these little 4 wires tell me we've got a stepper motor doing something. Don't know what yet. We're going to keep digging. You've got a couple of geared drive motors. I don't know if you can make that out there. If not, we'll pull it up on the close-up cam. Just a DC 24-volt motor. Little transformers doing something. Don't know. Don't know. Let's see how much closer we are to getting the cover off. Not close enough. Not close enough. I feel quite a bit of resistance. So, I am going to keep digging, looking for things that look like case screws, and pulling those out and off. And the hope is that we'll get to the point where we can see the entire inner workings before we have to start tearing apart the main frame, the structure of this thing. Again, if whoops. If I had any intention of putting this back together, I would be keeping note of how much force it took to take apart most of these screws so that I can apply that same amount of force to put them back together. Don't want to end up with something that vibrates itself apart. Alright, so it looks like we've got our first electronic circuit board. And this might be something that we bring up on our close-up cam. And all we have here is just a very simple LED. So that's our connector I just pulled off. We've just got a single light-emitting diode. Now, nowadays we've got much brighter LEDs. Probably would have put that against a white solder mask, that sort of thing. Nothing too exciting there, but you know, that's our first PCB. Resistor, connector, LED. This is actually a pretty expensive way to make this sort of board. Let's see if I can get a better focus for you. Everything that's done to a printed circuit board costs money. It takes time, and there's things. So when this thing was put together, there was, you know, a little bit of white silk screen. All right, that's cool. I mean, that's pretty typical. And a resistor was reflowed onto this. Most likely this board went through a infrared reflow oven. All right, that's cool. Happens to a lot of boards. But if you look on this side, there is a resistor, and then there's a through-hole part on one side and a through-hole part on the other side. It ends up costing money. I mean, that's two different processes that you have to go through. It could have been a wave reflow, selective solder. I don't know. I don't know how they put this thing together. I probably look a little closer, I could figure it out. But it all takes time. It all costs money. Why are we doing this? We could have put on a 90-degree angle connector, put it on the same side of this board, and done all of this in a single reflow cycle. Maybe even made this a through-hole component. Once you spin up first of all, it's always better to do surface mount technology if you can, because once you spin up the wave reflow or the selective solder machine, whatever it is, it all costs more money. But at that point, it doesn't really matter if you're putting 2 parts or 3, right? We're wasting money by doing that single little part all by its little lonesome. And I don't even know what's going on that side. I guess let's look a little closer. Maybe we'll learn something. All right. The thermoplastic screw is removed. Looks like we just have a hole, but man, I would have done this differently. I would have put the LED either a surface mount if possible. I would have made that surface mount if possible. If none of that was possible, I would have gone all through hole and put it all through on one side. Found a 90-degree connector. Basically eliminated steps wherever I could, and I just don't see that happening here. Also, I don't know what's going on with this 90-degree trace. That's just ridiculous. Just, you know, run a trace. I don't know. It just smacks of, let's just call it cheap, or it's either cheap software or an inexperienced engineer. There's really no reason to do all this 90-degree trace stuff. I mean, I don't know. Oh well. What are you gonna do? So, our case and cover are still on. Let's see what's next. Usually it's a little easier to get to the innards of these machines, at least the ones I've taken apart before, which aren't that many. And again, my goal here is to get the case apart but get the case apart in such a manner that y'all can still see what's in the middle. So let's keep taking apart the screws that we see. And right now I am pulling the ones by the presser foot where they would be, the stuff that's towards the spindle bobbin. There's a couple screws they give you to take apart just in case you ever properly tangle the spindle. Come on, little guy. There we go. So I just removed this little footing plate. So that's out of the way. And that shows us a few more machine screws that are attached to some piece of alloy. I don't know what that is, but they're kind of stuck pretty good. Might have to go get a proper tool to remove them. See, a minute ago I dropped my screwdriver. Let's see if that gets a little bit of a better capture on these things. Not so much. Well then. If we're going to be that way about it, we're just going to have to keep taking apart the things we can get to. And the amount of torque that are on some of these screws far exceeds the limits of that little torque driving screwdriver that I've got. I mean, that thing probably peaks out at about 30 Newton meters. These things are decidedly more. I don't know if they have some vibra stop on them or they've just been torqued down in the factory. But man, putting these things back together, if I had to put this thing back together with proper torque, I'd need a manual. They are just too tight. Well, I do see another circuit board. Let's pull this out and see what there is to see. Okay, another connector. And we will zoom in and focus. So what we've got here is a little optocoupler. I'm sure it's tracking the motion of the needle, seeing if it's up or down or that sort of thing. And all plated through hole stuff. Traces are huge. I mean, why not, right? No reason not to. And just a little bit of feedback. Looks like whoever designed this board took a different tack than the guy who designed the last one. Right, I've got the last one here. See how we've got parts on both sides of the board? Silk screen on both sides of the board. That all costs money that you can save. So see here, they didn't even use silk screen. They used copper for all of their lettering. And I mean, to me, whoever designed the board on the right is much less experienced than the guy who designed the board on the left. Put all the components on one side, got rid of the silk screen layer, got rid of the solder mask layer, right? Didn't need it. Forget it. Here we've got our silk screen and, you know, parts, everything. I mean, inexperience, experience. And you can't really tell that just... I mean, you kind of have to know this stuff. It comes from time. Time spent in factories, time spent designing, going to conferences. All right, we've got this thing trying to come open. It wants to. I want it to. Yeah, it's just making cracking noises. All right, so on the underside, we've got some screws holding things together that I missed. Here. We're going to try popping those and seeing what it does for us. I kind of feel like this is the housing for those transformers for whatever they do, but you know, we'll see. This one feels like the plastic housing for the sewing machine. And while we're here, I've got another printed circuit board. Little baby one. And I want to feel like this one was designed by the guy that designed the other one, the second guy. Oh, another optocoupler circuit. Right, same basic design. Is it the same board? It's pretty close. They moved the mounting holes a little bit, but same basic design. Silk screen one side. No use of solder mask. They got rid of that entirely. Using the copper to lay out the board identification markers. Real nice heavy traces. I mean, I've got nothing bad to say about this, except that maybe he could have worked with a mechanical engineer and, you know, made this all just one single board. I mean, they're really close. I think they could have worked a little closer together and made this one board instead of two. Right, look, I mean, those things are... Man, those things are almost identical. All right. Let's see what's next. Yeah. All right, that's out. Where are we at separating this case? It still feels like there's parts holding it together. Have we taken apart everything that's visible? I don't see any screws on this side. Whoops. There are plenty of screws on the bottom, but those seem to be related to the machinery and the mechanisms. Let's see what else we can do. Sometimes they'll hide screws underneath pieces like this. These are extras, you know, put on after the fact, adhesived in. If we wanted to be careful about removing it, we could apply a little bit of heat, but again, we're not really worried about getting this thing back together. And there's nothing there, but see, I mean, it's just adhesive. You'd take that off the same way you would a cell phone. Well, nothing is popping out at me as being responsible for holding these plastic pieces on. So we're just going to keep taking off things that are visible, you know, visibly attached, and it could be that, you know, metal pieces are held to those, and once we release them, this thing will fall off. I doubt it, but that gets us, everything gets us one step closer. Yeah, cracking, never good. But again, we're not going back together. So, all right. We'll just keep cracking these things, see what happens. Big screws, lots of force. Small screws, tiny force. I mean, I haven't looked at any of these closely, but pretty common for machinery to be metric. Makes designing fabrication a lot easier. I mean, most stuff's made outside the States anyway. And the United States is the only country that has the antiquated and arcane and difficult to keep track of screw numbering and sorting system threads. 1032, 1024, you know, coarse and fine. Quarter 20, quarter 28. It all gets terribly confusing. You go metric, you know, you've got 6 millimeter diameter by, you know, 0.5 threads per revolution, or, you know, 1 or 0.75. But it's all very clear and very easy to machine. You don't need conversion tables. All right, let's get that screw free. What did I just clip onto? I don't know. There we go. So just some metal plate. Nothing too exciting. All I'm doing here is looking for anything that could be remotely connected to the housing. I want to get the housings free so we can look at the electromechanicals in this thing. Looks like we're making progress, but there's still stuff. There's still fasteners holding all this together. Right now, I am really glad that I am not a sewing machine repairman. Although, if I was a sewing machine repairman, I would have a manual, and I would know exactly how this comes apart. Roll pin. I'll tell you this, there are times when the way I take things apart involves a hammer or a saw. And right now is one of those times, except that I don't have a hammer or saw handy, so we're going at this the proper way. But man, these things are torqued on. You would really want a manual so you knew how much torque to put all of these screws and fasteners back on with. Because they have certainly been fastened with man, no. Okay. Well, we're going to keep trying. We'll get there. At some point here, we're going to have to transition over to sockets and hexagonals, but I wouldn't expect sockets and hex drivers to be holding this case on. What am I missing? I mean, it could be snapped in place for sure. Always good when stuff just falls off, right? That was a thing. I don't know what that was. But we don't need it. We want to see electronics. Okay, just gonna keep taking stuff off. Maybe we'll start working down to where I want to be, which is case free. Come on. Nope. Okay. If that's what we're going to do, then we will just use the Leatherman. I guess we'll take this post out. To gain access to that screw. And then see if this actually unscrews. This looks like some sort of a cam arm that positions the sewing needle or repositions the sewing needle. However, the clip and some of the other things make me think it's not going to be so easy to get out. All right, where are we? All right, success. There goes the back side of the case. Well, isn't that fun? We're making some progress. All right, we're looking at the back side of a very simple circuit board. Let's see if we can get this thing out of here and see what we're looking at. Seems to be the main control board, the brains of this thing. All right, what do we got? What do we got? We're stuck. There's more than this. So, I am going to rotate this little locking pin backwards. I mean, there's a good chance that breaks off. There's a couple of these, actually. So that's how they saved $1 on the circuit boards. They didn't actually mount them. They just did a little twist gate thing going. And it looks like can remove that. big thick wires, so probably power, and it's going to be a minute before I can get to the rest of that. So, all right, progress. Okay, so what's holding this on? What is giving me grief? I mean, there's still plenty of screws and nuts and bolts and all that sort of thing. And some I can see are connected to the case. It just seems, I mean, I could of course be wrong. It just seems like the screws and whatnot that I see are doing other things. Obviously something is still holding this case on. So let's just keep tackling those, and eventually maybe we'll get to the right ones. That one looks like it is connected to the case and the housing, and it is torqued on relatively strong. Come on. Nope. There's a number 2, it just spins. There it goes. Let's see if that had a dual. No? All right. So we will continue to dismantle things that are tangentially related. And maybe with luck, stumble upon even if there's nothing electronic to learn from this, which, by the way, there's always stuff to learn from it. But even if there isn't, what you're learning by taking apart the mechanical is a second discipline. You're learning how people do things, how they engineer complex movements, how they incorporate various materials. I mean, for example, right now, I just pulled off the front of this. I mean, whoever engineered this incorporated spring steel. This is a gauge that had a switch on it. Often you'll use this for button zippers, buttonhole. I mean, just different things. It works with the presser foot. So you just never know. But again, what I want to do is get that front clear. I want to look at the circuit boards. And since we are fresh out of screws that look like they connect the front, we are just taking out all sorts of screws with the hope that eventually we're able to release the front. This is something where a service manual would be incredible. Okay. Well, there we go. A little brute force. We got some circuit boards. We'll look at those in just a second. Let's see what we got in here. So this thing obviously has some circuit boards. I am going to release the connectors here. Get rid of the wire ties so we can withdraw these. Hopefully do that without severing any of the wires. A lot of connectors on this thing. Trouble with that is that connectors are expensive. So anytime that you can use a 4 position instead of a 2 2s, or that you can, you know, just have things soldered right into the board, you're usually going to save money. Not always, just usually. So let's go ahead and remove these. It's actually quite a few screws. Holding this thing in. We'll see what's on the back side of this, but looks like there's a carrier board and then a PCB attached to maybe the carrier board. We'll see. Oh, okay, so there's a plastic protector board. We got the brains. We'll look at that in just a second. A couple interesting things they have going on there. It's a clean looking board, I mean, just on first inspection. Looks like whoever designed that had a little bit of PCB experience. A lot of solder. Looks like this thing went through a wave reflow. It's actually not that old. This thing's 10 years old. I wonder why it failed. Interesting. And we will just keep taking things out. Alright, so another board we'll look at in just a minute, but looks like we've got just 3 opto... how weird. Remember how I said earlier I would have just done all through hole since you were doing through hole? Well, here we've got 3 optical sensors all in a row, and check that out. 3 through-hole resistors. So this is a dirt cheap PCB. You know, no solder mask. It looks like there's a clear lacquer layer, but again, different trace designs than before. How weird. Obviously, I mean, this is a team effort. I mean, we've got 3 distinct styles of design. You know, here's the second one I pulled out. I want to say this is the first. I mean, obviously, I mean, to my eye anyway, we've obviously got different designers, different experience levels. Interesting, interesting. Well, let's keep digging. We now have access to pretty much everything. And more boards. Well, who doesn't like looking at a good circuit board? So yet another circuit board. Copper indicators, no solder mask. So maybe they just had the newbie on that one board. I don't know. I'm back to using the Leatherman. We really don't need to know how much torque to butt on these things since we're not putting this board back together. It's all coming apart. But I still haven't seen anything that indicates to me why this sewing machine failed. I mean, who knows? Who knows? But it's always nice to know why things fail. All right, so I got a trick for you here, something you guys might like. I have some screws that I can't get out. They are these tiny little guys right there. Well, van pliers are the solution to that problem. These things have threads in the tip. So you just grab on and twist. And all you have to do is get them going a little bit, and then you can catch on with whatever your other tools are. And they'll just twist right out. So how fun is that? So there we've just released a limit switch. There it is. All right, as we continue the disassembly, van pliers are great for grabbing a hold of tiny, well, I mean, grabbing a hold of anything that's around, really. I mean, screws, nuts, bolts, they don't care. And again, we're not really tracking torques since we don't have to worry about ever putting this thing back together. So we're just going to keep going through. Finding screws and bolts, extracting them. By the way, if you ever want to cause trouble at a fastener convention, sit down at a table and ask people what the difference between a screw and a bolt is. Seems like everybody's got their own opinion. All right, so a few minutes ago, I pulled apart a triple optical encoder. Right, here it is here. And this is what it was connected to. Let's see if we can zoom in on that. Right, so we had a triple-headed optical encoder. And here we've got the three heads. So this forms essentially a, you know, some version of a quadrature encoder. I don't know what kind of, what kind of accuracy this thing required, but it's got 3 gates, and those 3 combined create some sort of a code that the computer understands and decodes. All right, let's see if we can't yank whatever that is since we're here. All right, those 3 are free. Don't know what they are, but they are done. Let's back up a little and keep going. All right. Not a whole lot of mechanicals left on this thing, which is fine by me. Because again, what we're looking for are the electromechanicals. So if we have a really cool bearing or you know, some sort of a electromechanical encoder, we would much rather have the electromechanical encoder, at least for this channel. So we're going to keep taking stuff apart and see where we land. The good news is that tomorrow is trash day, so I won't have these things sitting around for ever and ever and ever in my life. Well, what else can we remove? You know, I'll be honest, I was actually expecting quite a bit more sensory in this. There's not. Which is fine, I just was expecting more. We've got some motors, we've got sensors. There's not as much feedback as I would have expected, so a great deal of this must just be the designers assuming that things are going to do what you asked them to do and go from there. Is the needle up? Is the needle down? Is there rotation as you want rotation to be? All right. See if I can't yank this roll. No, this roll pin does not want to come out. I'm going to have to smack it with something. Which is understandable. I mean, it's a sewing machine. It needs some amount of force. Okay. So we've got a keeper. That's free. I don't really feel like properly withdrawing that roll pin, so I'm going to use some compound cutters to Nope, not enough. Not close enough. Oh well. Let's see if we can't keep making progress to that end, though. Even if we can't yank it all out that way, we'll see what we can do. Come on, little guy. So there's a little bit of plastic circuit board over there I want to get to. But to do that, I've got to withdraw a couple of these quick connectors. Alright, so I've got a control board out, and we will certainly look at that in just a moment. But before we do that, we're going to withdraw the power input and switch. Boy, I tell you, my circuit board is quite the mess right now. Okay, well, I'll tell you what, we're just gonna trim all these guys. Get them released. Power switch, I mean, I don't know if you can tell, but those are some tiny wires. That must be running some sort of a signal. There's no way they're running power through that. Okay, we're making progress. This is the drive motor. 24 volt DC. it just, I mean, its job in the world is just to spin. And that complicated set of optical sensors is, whoops, it's there to figure out where this thing is as it spins. So here's our drive motor. I mean, nothing particularly interesting about it. It's timed. You know, you can see the teeth there. So it's keeping track of where it's at and whatnot. We're just going to go ahead and pull off. For some reason, they've isolated it from the rest of the chassis. Maybe that is a signal integrity issue. I don't know, but you know, they have these plastic bumpers, and they're hard plastic, so I don't know what those are for. So anyhow, motor 1, there we go. Hiding underneath here, I don't know if you can see it, but there's another motor. This one's a stepper motor. So we don't know what this one does all by itself, but we do know that this sewing machine was able at one point to do some manner of embroidery, fancy stitches. So this must have been, oh man, doing some deflection of some sort. All right, let's go back to our actually, you know something, let's go to a smaller screwdriver and see if that works first. We have a very, nope. How about this one? Got a very small aperture that we can put a screwdriver into and turn things, which is good. I mean, we can get stuff in there to do it. But man, a lot of these things are just torqued down like you wouldn't believe. Okay, so there, that releases the optical encoder and the motor. Right, here's dropping stuff. Here's the optical encoder that was on that one. And there's just this tiny, tiny, tiny hole. We need to zoom in on that, I think. Where is our, right there. So here is our shaft with the optical encoder, and the optical encoder is that tiny, tiny rectangle. You can't really even see it except if I get the light just right. Right there. Right, that's what this thing is spinning around and locating. So it probably, you know, locates it within a degree. Well, a couple degrees. That's a pretty big hole. Okay, so everything that's left is mechanical. I just want to double check, but it looks like everything that is left in this machine is mechanical. And that is outside of our purview, right? We are electrical. So we're going to set that aside. Interesting stuff. But we don't really care. What we care about is what's left here. All right, so here we've got a board, and it is certainly a power board. Well, sorry there, little MOSFET, I just tore you off. But this gives us an idea of what these guys are doing. And we've got yet another printed circuit board style. So this is a different core material, different dielectric, different silkscreen color, right? We're black on yellow now. There's nothing, no solder mask. I mean, it's a pretty decent silkscreen layer. I kind of like that. But everything, well, not everything, almost everything is through hole. It's all on one side. I do see a little discoloration here. I guess that's around one of the transformer pegs. I wonder if the power just went out on this thing. This would be if you had the repair manual and a little more knowledge than I do. This might be the board to replace. There's, you know, some electrolytics that can go. Resistors sometimes, if they're not properly rated, you know, they'll burn up. Huh. I don't know. Nothing on this is screaming at me, you know, here's why this board failed. This is probably a pretty expensive little board, but they've done everything they can to minimize cost. With the exception of this, we've got a surface mount IC on the back side. And I don't know if we can... No, we can't really zoom in anymore with our current camera setup. Okay, we'll have to get a microscope going, camera going. But you can see where they've separated the high voltage and low voltage side. Anytime you see slots in the board, well, not anytime, but mostly when you see slots in the board, it's for creepage and clearance, trying to prevent the voltage from carbonizing a path through the dielectric and creating a short circuit situation. Interesting, interesting. All right, getting over to our control board. Totally different designs. Different manufacturers. Different people made these boards. Here is our power board. Here is our logic board, essentially. I mean, whoever did this went to great lengths to make it look pretty. And they did a pretty good job. There are components on both sides, something that you want to avoid if you can. I mean, huge globs of solder. So this thing went through a wave reflow. That's not hassle. That's, I mean, maybe you probably can't tell from the video, but that is certainly not hassle. That is millimeters off the surface. So, I mean, something just globbed onto the stuff. So you've got control circuitry that has to get wave reflowed on. That's interesting. They went with a hatched ground plane over on this side of the board. Don't know why. But I mean, everything's nice and clean. Whoever did this, to my eye, certainly had a bit of experience with what they were doing. This here is hassle. Hot air solder level. I mean, it's flat. It's pretty much in plane. You can kind of make out some of the subsurface features as compared to this, which is just globs of tin in lead. Huh. I wonder why they did the hatched plane in that area. I mean, if we get bored later, we can look up this particular IC. It's a through-hole. It's rare that you see a through-hole component that has capacitive issues that would require a hatched plane, but they certainly went to the effort of hatching the plane around that particular component. Gosh, I don't know why. Interesting, interesting, interesting. All right. Well, that's pretty much it. We've taken apart the whole darn thing, learned what we can learn, saw a couple design styles, and with that, I mean, I don't know if there's that much left to look at. It was kind of fun. I guess we missed this piece of aluminum, which had some MOSFETs that I just tore right off the board. Sorry about that. They were using these for... Had I looked a little closer, I would have seen those screws and I could have taken them out. It wouldn't have mattered. All this is going in the trash. But it looks like they're using that giant piece of aluminum as a heat sink, which is pretty typical. So, with that, that's it. It's been fun. It used to be a sewing machine. Oh, we missed that board, but maybe we'll look at that a little bit more tomorrow. But my suspicion is that whole board is just controlling that LCD. I mean, we could look a little closer and see if there's anything else to see, but I doubt it. So, whoops. With that, it's been fun. I'd say this warranty is void. Thanks for joining me on Mark Voids a Warranty. We'll see you next time. Take care. Bye.